Good afternoon. My name is Chuanhua Duan from Mechanical Engineering. It's my great pleasure to introduce our research works related to energy and sustainability. So I would like to start with my talk with a quick introduction about my lab. The Nanoscale Energy and Fluid Transport Lab. It was built in 2012. So in the NEFT lab, we study and we focus on study and application of energy and fluid transport in and around nanometer-sized objects, including three-dimensional confined nanopore, two-dimensional confined nanotube, one-dimensional confined nanochannel, and mesoporous mediums. So we study fundamental transport in those confinements and using our new understanding to explore new applications in water desalination, energy conversion storage, electronic cooling, point of care, and building energy. So in the following slides, I will show you several examples, nanopore-based example on energy and sustainability. So the first one is exploring kinetically-limited evaporation for nanoporous membranes for sustainable electronics. So when we talk about future electronics, we always talk about like devices, the smaller, thinner, and lighter devices, the high density of transistor. This inevitably causes ultra high heat flux. So the corresponding thermal failure is actually the number one obstacles for future sustainable electronics. So to address the thermal issue, we need better cooling technologies. So far, the best cooling technology is liquid evaporation-based nanoporous membranes. So, but the performance of those liquid evaporation-based technique is limited by the evaporation kinetics at the liquid vapor interface. We don't know what the current limit is, let alone to develop better membranes to achieve the ultimate performance. So in my group, we have developed ways to measure and study kinetic-limited evaporation from single nanopores, okay, for the first time. So we use our technique to measure evaporation kinetic-limited evaporation from different nanopores with different confinement, materials, and pore density. So we discovered temperature dependence and confinement dependence, where you try to use it to develop the next generation of nanoporous evaporative devices. So the second topic is regulating mass transport through nanopores for sustainable carbon footprint. So we all know that the world needs AC, right? Which cause lots of basically consume lots of energy and cause significant carbon footprint. But what we don't know is most of the energy consumption by air by AC in like high, medium, or relative humidity is consumed by the vapor-based latent cooling loading. So to address this problem, we really need to get an energy efficient active or passive humidity control. So one way to think about it is using vapor diode or vapor transistor that we can control vapor transport at will or in the preferred directions. So one way we can solve this problem is to learn from the literature about stimuli responsive mass transport, okay, that in cell membranes. So in our lab, we try to replicate this technology using nanoparticle blocked nanopores. So we have developed several ways we can do reversible and complete gating. So we try to use the control vapor transport and develop better techniques for building energy. So the last one is novel nanoporous membranes for surface heating membrane desalination. So membrane desalination is a promising water desalination method. This method is based on a hydrophobic membrane. By heating the feeding side, so only water vapor can go through the membrane such that selective transport is achieved. The big issue of this technology is like you are heating up the whole feed, the side, but only surface water is evaporating. So lots of energy is wasted. So recently, the new technology is developed based on surface heating, where we only heating the surface water so that we can save energy. So in our lab, we're currently doing two things. We're trying to develop a scalable, basically conductive layer based on laser-induced GO to get a better surface heating layer. In the same time, we try to study a membrane with organized structure to explore the maximum performance. Thank you.